My name is Sriram, and today I will be teaching you this course. Object-oriented systems have emerged from several research threads. The fields of databases, programming languages, artificial intelligence, and graphical user interfaces have all contributed to the emergence of object-oriented systems. The fields that have necessitated the capabilities of object-oriented systems are computer-aided engineering, computer-aided software engineering, office information systems, and graphical user interfaces. Today, I will be providing an overview of this course, and this course is divided into 5 modules. In Module 1, I will give you an overview of the technology of object-oriented systems. In Module 2, I will talk about object-oriented databases. In Module 3, I will talk about object-oriented software development. Module 4, I will talk about commercial systems. And finally, I will share with you how we have used object-oriented systems in a number of applications in our laboratory, which is called Intelligent Engineering Systems Laboratory. The overview. I will start this overview with tracing the evolution of object technology. Then I will discuss the vernacular of the object-oriented systems, that is the terminology. There are several definitions that are available in the market right now, and I will be giving you a definition that is my definition of object-oriented systems. I will talk about classes and objects, message passing, inheritance, and finally I will summarize. First, the evolution of object-oriented technology. This particular evolution I will divide into 4 decades. First, some 60s to 70s I will call the early period. From 70s to 85s I will call the medieval era. From 85s to 90s I will call the coeval era, and from 90s onwards I will call the future. And I will place an emphasis on 3 areas, that's the input, program structure, and the storage. The early period, the 60s and 70s, punch cards were used to input programs and data. To make any changes required considerable amount of labor. Many organizations hired punch card specialists whose sole task was to input programs and data on punched cards. For many of you who have used punch cards, you must have had the problem of dropping the punch cards and not numbering them. I had that problem, and it's a very, very painful task, as you know. In terms of the program structure, there was no notion of the separation of data and programs. And the storage, magnetic disks and tape drives were used to provide the persistence. Several research organizations at the same time were involved in the development of programming languages such as Smalltalk, Simula, and a host of other object-oriented programming languages. In the second period, which is the 70s to 85s, the advent of time sharing and teletype terminals resulted in a major shift in the use of computers. Command language interfaces were used for inputting data, while line and screen editors were popular for text editing. As the size of the programs increased, the divide and conquer paradigm was used to reduce the complexity, and this was also known as procedural abstraction, where we had a main program, and the main program was divided into several subprograms which called the data. And in terms of the storage, there was a need for managing large amounts of data, and this resulted in the development of database management systems. In the late 60s and early 60s, the network and hierarchical database systems were widely used. Cart's influential paper on relational database systems has brought the relational data model into prominence. Cart's primary aim was to improve productivity by providing data independence. However, the structure also makes the relational model fairly inefficient for complex information processing such as case, CAE, and so on. An important outcome of Cart's work is the structured query language, or SQL, and this provided an easy means for the users to input query languages in a declarative manner. At the same time, lot of research was going on in various universities and the notion of abstract data types evolved, and in particular the work by Barbara Liskov at MIT provided pioneering work in this way. For she developed the language called CLUE, and CLUE introduced the notion of abstract data types. In the 85s to 90s, Xerox PARC research on the Alto computer resulted in advanced graphical user interfaces. However, this particular work, these techniques were not utilized by Xerox and put into practice by the Macintosh computer system. In terms of the programming structure, a major trend in programming style has been the shift towards an object-centered view or the data-centered view. The object-oriented programming style implements the notion of abstract data types, which was put forward by Liskov and other researchers. And there is a direct mapping from the object-oriented programming style to the object-oriented database systems. So we see an emergence of object-oriented database systems in areas such as engineering and office information systems. However, you must note that there is still a lot of relational bases developed out there, and these systems continue to dominate, but I see an emergence of the object-oriented database systems. What about the future? Where are we going in the future? The future, in terms of the input, we will see, and in addition to the graphical user interfaces, things such as voice, vision, and natural language communication modes may become very popular. Object-oriented programming styles will be dominating the programming landscape, and in terms of the databases, we might see a mixture or a hybrid of relational databases and object-oriented databases emerging as the prominent role. Now, I will talk about some basic concepts of object-oriented systems. Especially, I will focus on the vernacular of object-oriented systems. The vernacular. There are 4 basic mechanisms for any that a system should have to claim to be object-oriented. And these 4 mechanisms are defining objects, forming taxonomies, sending messages and methods between objects, and implementing inheritance or allowing inheritance process. Associated with these key basic mechanisms, we also have certain key concepts such as overloading, abstraction, polymorphism, dynamic binding, encapsulation, and persistence. As we are talking about these basic mechanisms, in the same time we will be talking about the key concepts. So from time to time I will be giving definitions of what these key concepts are. There are a number of related terms which are used in other fields such as artificial intelligence and graphical interfaces. These terms are frames are used quite a lot in the AI area. The term called widget is used in the user interface area, and we also see things such as events, triggers, signatures, and agents in the artificial intelligence area. First, let me talk about what an object is. Objects combine data and procedures. That means objects have both structure, state, and behavior. Objects respond to messages, and objects have unique identities. Now, these are the 3 characteristics of an object. There is a small cartoon here which shows the nature of objects. Here is a person who says he is from Bank of Credit and Commerce Incorporated. This is a particular object which is sending a message to another object who is a salesman. This object, the minute he receives a message saying that I am from BCC, immediately responds with another message, how about buying some Acme bonds, which are junk bonds. So to summarize about objects, objects have structure, behavior, and identity, where the structure encompasses all of the properties of the object plus the current dynamic values of each of these properties. And the behavior tells you how an object acts and reacts in terms of the structural changes and message passing. Identity is that property of an object which distinguishes itself from other properties or other objects. So, let us look at some typical objects. Here are some typical objects that I am going to illustrate the concepts of object oriented programming using these objects. The first object here is Mary's car. It is a unique object. Then we have Ram's car, we have Jack's car, we have Red's truck, we have John's truck, and we have Hussein's truck. Let us have a closer look at Mary's car. In terms of the structure, we can define Mary's car as shown in this particular slide. Mary, there is a owner, and the owner is Mary. The model name is Benz. The manufacturer is Daimler-Benz. It has an ID, and the ID is the vehicle ID. For the purposes of this talk, I am using 999. There is a model year which is 1989. The exterior color is red. The interior color is brown. The cost of this car is $40,000. There are a number of components that constitutes this car, body, drivetrain. We will come back to this subparts later on. And this constitutes the structure of this Mary's car. And what about the behavior? Well, there are several things we can do with this structure. How do you access the elements of Mary's car? One way to do it is to make all the attributes public. And the other way to do is to provide an interface to get into this particular structure. And here is the interface that we provide. To get the model name, we cannot get it directly, but rather we use we can use an interface where you send a message to Mary's car, get model name, and associated with that model name there is a procedure which gets activated, and we will come to that in a minute. Similarly, to get the ID, we have a message that we send to Mary's car, get ID, and there is a procedure called get ID which gets invoked. And I have also introduced another behavior here called diagnose, and this behavior will tell you how to diagnose problems with Mary's car. So, now we have the structure and then we have the behavior. The structural aspects here are define the overall physical structure of this car, and the behavior will tell you how to get values from the structure. In addition to that, it also does things like diagnose and a number of other things that can be added here. Note that in this particular slide, I have added something called private and public. What this means is that this particular private part is hidden from the public interface. So, to get any values from the private part, one has to go through this public interface. So, this is said to be encapsulated, and we will come to that in a minute or so. Now, let us have a look at the behavior aspects of Mary's car. So, the way it works is the following. You send a message get ID to Mary's car, and there is a procedure called procedure get ID which gets invoked, and that procedure will do something and go and get the ID. Imagine if someone were to ask your salary, for example. It all depends who asks you for your salary. If the IRS asks, you give one answer, and if someone who is a potential employer asks you a question, you give another answer. So, depending on who asks you the salary, you give a particular response. So, that particular behavior now can be encoded using procedures of this sort. So, you can hide the internal details of the implementation from the external interface as such. There is another thing we can do with this car with Mary's car is to send a message called diagnose. When you send a message called diagnose to Mary's car, what happens is a procedure called diagnose BENZ will get invoked. Now, this procedure is not an ordinary procedure, but this procedure is a knowledge based expert system. Now, look at what we can do now. We can add artificial intelligence or intelligence, some kind of an intelligent behavior along with a particular object, and this intelligent behavior can be encoded in knowledge based expert systems. Where knowledge based expert systems are computer programs which incorporate human expertise. Typically, these systems contain the following components: a knowledge base where you have knowledge encoded either in rules are facts or objects. A context mechanism, which can be viewed as a short-term memory, where you have the current working aspects in the short-term memory. Sometimes this is also called working memory. And then we have an inference mechanism, which actually is the problem-solving strategy. So let's have a look at the knowledge base and how we can encode rules. These knowledge bases offer you a flexible way of encoding human expertise. Here are some rules for diagnosing Mary's car. The first rule says if problem equals dead battery or problem equals bad ignition system, then you have found that the particular problem with that car. How do you find whether the problem is dead battery? We can write another rule which says if the init problem, that's the initial problem, is starting system and headlights are dim or dead, then the problem equals dead battery. And how do you determine whether the problem is with the init starting system? We can determine it using the following rule. If the ignition key is on and the engine state is not turning over, then the init problem is equivalent to starting system. Now assuming that our knowledge base has these three rules. Now however, we can add, suppose we find a new problem with the car, we can add in very easily as is shown in this particular slide. We are adding a problem equals bad starter, and then we add another rule into this process where if init problem equals starting system and the headlights equals on, then the problem equals bad starter. So using the knowledge based framework, what we can do is incrementally add knowledge to the system. So we have objects have behavior, and the behavior can be encoded as a knowledge based expert system. In the knowledge based expert system, we can encode rules like this, and in addition to that, we can also add several inference mechanisms such as forward chaining, backward chaining, hierarchical refinement, constraint handling, qualitative reasoning, case based reasoning, neural processing, and a host of other things. If you want to know more about knowledge based expert systems, there are a number of texts available, including the one that we are putting out from our laboratory, and if any one of you is interested, please feel free to give me a call on that. So to summarize so far, what we have done is we have taken Mary's car and defined a structure to Mary's car and a behavior to Mary's car, and we said that we can have several kinds of behavior. One kind of behavior to access into the elements of Mary's car, and the second kind of behavior which will provide us things such as diagnosis, maybe design, and a number of aspects of Mary's car. Now associated with, for separating this private and public interfaces, we have the notion of encapsulation. What is encapsulation? I can show you encapsulation with the following slide, where now we have the public interface here shown outside in this cell, in this capsule, and then we have internals, which show the attributes. Now the internals here are, for example, the ID, which is 999, and model name, which is BENZ. So the only way Oz can get into the model name is to get the model name is send a message called get model name to Mary's car, and when Oz sends the message get model name to Mary car, this get model name will go and get the model name for BENZ car. So it's called encapsulation because you are encapsulating information here, and the only way you can get into this information is through this public interface. It is like a capsule, like a Tylenol capsule or some capsule like that, where you don't know what the internal details are. The only way you can get to the internals or the innards is through this public interface. So the innards are hidden from the public as such. However, if you look at Mary's car, it's kind of obvious that we don't really need to hide model name as such, because model name we can easily see from looking at Mary's car. So what we can do is we can take this particular model name out from the structure, from the private part, and put it into the public part. And similarly, what we have done here is to add in a new behavior into the private part, and that this particular behavior you don't want everyone to see. So from some public interface, I can go into this private behavior as such. So, now what we have done is we have divided Mary's car into a private part and a public part, and in the public part we have both structure and behavior, in the private part we have both structure and behavior. So, the structure and behavior now can be encoded in both the public part and the private part. There are several variations of this process of encapsulation, and I will give you one variation. The one variation I showed you just now is this one, where now Oz can go and get the model name directly from Mary's car without sending a message. Now, the only disadvantage of this is now if these variables are public, anyone can access these variables. It's something like my lawn, for example. The reason I mow my lawn is that it's a public variable and people see my lawn all the time. They not only see my lawn, but they also modify my lawn by dropping in various elements which I don't want to be dropped on my lawn. So, the lawn is a public variable. On the other hand, the things in my house such as my living room, my bedroom, and if someone wants to know what furniture that I have in these rooms, they have to ask me. They can't just come in, and they cannot have a public interface to that. So, the public variables are public to everyone and you can make changes. So, there is a danger to that, and the private variables are private, and the only way to get into the private variables is through the public interface. Some languages such as C++ offer a kind of a variation for this encapsulation. There is another variation where you have the private part, a protected part, and then a public part. And we will see when we talk about C++ in module 4, we will see how this thing is implemented in that particular language. C++ is one of the popular object oriented programming languages, and we will come back to that in module 4. Let us now look at Jack's car. In a similar way, just like as we have defined Mary's car, we can now do the same thing to Jack's car. Now, look at Jack's car. Jack's car is very similar to Mary's car. The owner is Jack, the ID is different, 949. The model year is almost the same. The interior color is a little different. The cost is about $2,000 more. Jack has some additions onto it. Otherwise, things are the same in the public interface and private interface. So, what we have seen here is some common elements between Jack's car and Mary's car. So, what do you do with that? Here is what we do. That is the next part we will discuss. That is the classes and instances. So, what we can do now is to take Mary's car and Jack's car and abstract out the common information and form a new car called BENZ CAR. And here is an example of BENZ CAR. So, we have taken the abstract properties and the behavior here, and we have taken the common elements and placed them in the BENZ CAR. So, here we have owner, the ID, model year, interior color, the picture, which now we have added a new element here called picture, which can point to a BENZ CAR dot picture. Now, we can show picture on the screen too. In terms of the public interface, the model name is Benz, the manufacturer is Daimler-Benz, and what we have done is we have given it a default value called black. So, in case if you get information from the BENZ CAR, we will get if you ask for the exterior color, we will get the answer as black. Interior color, we have left it open, and then we have added in a new behavior element here, which is to design BENZ CAR. I am doing this process in a bottom-up manner. I can probably do it in a top-down manner too. Okay, now let us look at Mary's car. What we do now is to define Mary's car as an instance of BENZ CAR. Mary's car, we don't copy all the things which are in BENZ CAR, but only those parts that are to be modified in Mary's car. The things that need to be modified are the instance of which is the same BENZ CAR. The owner is Mary, ID is 999, model year we have changed to 1989. The interior color is brown, the cost is different. The components are the same, but the subparts in Mary's car are different than the subcar parts in other cars such as Jack's car. So, we have modified that, and the exterior color is red, as we have seen before. In a similar manner, I am going to define Jack's car. Now, Jack's car is an instance of BENZ CAR, and some of the attributes have changed values, such as exterior color. Other attributes, there are no changes, so we don't need to make any changes in Jack's car as such. So let's look at the taxonomy of the cars as such, which was shown in the previous figure. So we have Hussein car, which is an instance of the BMW car, Jack car, which is an instance of BENZ car, Mary car, which is an instance of BENZ car, Ram car, which is an instance of Toyota car. So we are defining two new terms here. One term that I am going to define is an individual object. Individual objects are objects which cannot be further classified as such, or which cannot be further instantiated. Again, this is a definition which I am giving. This is my view of what the individual object is. Now, these individual objects are grouped into what are known as class objects through this relationship called the instance of relationship. So, the instance of relationship links individual objects to the class objects. So, we can take several individual objects and then group them into a class object through the instance of relationship. So, this aspect going from the individual objects to the class object is a process which is called classification, and the relationship classification is denoted by the instance of link. Then we can take these class objects such as the BMW car, the BENZ car, and the Toyota car, and we can group these class objects into another class object called a car, because they are all cars, as we know. And that relationship, that the relationship that links these class objects into another class object, which is the car object, is called generalization. So now we have I have introduced two types of relationships: the generalization relationship and the classification relationship. The classification relationship maps the individual objects into the class objects, and the generalization relationship generalizes the class objects into another class object. The generalization relationship is generally given by ESA term. Now, the process going from here to here is called specializations. From the super element class, which is the car, to its subclasses is called specializations. Similarly, going from the class to the individual objects is called individualization. So, we have classification in this direction, we have generalization in this direction, we have specialization in this direction, we have individualization in this direction. This relationship between individual objects and the class objects is denoted by the instance of link. The relationship between the class objects and another class object is denoted by the ESA link. In some languages, the ESA link is also called super and AKO, and several other terms are used for that. But I will be using throughout ESA to denote the generalization concept and instance of to denote the classification concept. Now, the class car now is a vehicle. The vehicle now is a more, we'll come to vehicle soon and see how the vehicle looks like. We have all the elements which are common to all the cars, if you go back to the previous slide, like the BMW car, the BENZ car, and the Toyota car, we abstracted it into the car level. Okay, now you might ask a question: why is that I don't see those particular attributes around here? And I have also made one more change here. If I go back, that is between the BENZ car and the car class car. If you look at this particular behavior, you see that it's now called diagnosed car and not diagnosed BENZ car. This is particular. So this is peculiar to class car itself. Well, to clarify that, let's have a look at the vehicle taxonomy. If you look at the vehicle taxonomy now you can see that the cars, trucks are grouped into the super class, which is the vehicle given by this ESA link. So we can now create these kinds of taxonomies for objects in other domains too. So, let us have a look at the class vehicle, which is the structure, and then let us have a look at the behavior later on. So, the structure kind of looks like this, which is similar to the structure of car, which is similar to the structure of BENZ CAR. We have owner, ID, model year, interior color, cost, picture, components, subparts, and then we have some behavior encoded here. So, the private part of this particular vehicle contains both structure and behavior. Then we can now, as we have done in the previous slide here, the class car is defined is a vehicle. So, what happens is that this particular class car inherits all the information from this vehicle. I am describing this in English like terms right now, and as we go further in the day, I will also tell you how these concepts are implemented in languages such as C++ and in database systems such as object store. The public interface is shown as follows. We divide the public interface of the vehicle into several areas, the structure and the behavior now can be grouped into access behavior, problem solving behavior, and display behavior. The access behavior here is shown by these terms get ID, get owner. The problem solving behavior is shown by diagnose and design, and the display behavior is shown by this display, and we can keep incrementally keep adding more and more behavior or more and more attributes as we refine these things further. What we have introduced here is a key term called abstraction, where abstraction involves concentrating only on the essential structure and behavior and leaving the details further. So, what we could have done is we could have defined the abstract class called vehicle, and then we could have put in more and more detail as we go into the class car and BENZ CAR and Mary's car. So, as we are going down the hierarchy, we are adding in further detail. So, this process is called abstraction. As I have promised before, I will be kind of talking about the key concepts as I am talking along the same terms here. So, what I have done so far is to introduce two key concepts, abstraction and encapsulation, and now I will be introducing the other key concepts. The next thing I would like to talk about are messages and methods, because objects, as you have seen, respond to messages, and we have given you an example before how a particular object responds to particular messages. So, we also shown in the vehicle class how we can group these messages into various protocols like the access protocol and the display protocol. Now, the object oriented systems support a concept called polymorphism, where the same message sent to objects at different objects will invoke different responses. So, now we are introducing a new term called polymorphism. For example, in this particular case, if I send a message called diagnose to vehicle, I would invoke the procedure called diagnose vehicle, as we have seen before, and if I send a message called diagnose to BENZ CAR, a procedure called diagnose BENZ CAR will be invoked, and these two things have different behaviors as such. So, the same message sent to different objects invoke different kinds of behaviors, and this is called polymorphism. So, to summarize, polymorphism is a feature by means of which data and methods assume dynamically various forms during run times. The next aspect, and a very important aspect of this process, is the inheritance process. So, in the vernacular, we have defined the basic mechanism. We are discussing the basic mechanisms, and then I have said there are 4 types of basic mechanisms that have to be in any object oriented language: defining object, forming taxonomies, sending messages, and finally defining inheritance. Inheritance is an extremely powerful idea where classes and instances inherit both behavior and structure. Inheritance supports sharing, overriding, and specialization. We all inherit certain characteristics from our parents. We inherit structure, we inherit behavior. Often many people, depending on which side of the family they are, they will tell you, you resemble your father or mother. Now what does this mean? This means that you structurally you kind of look like that. Similarly, they might even say that you walk like your dad or you walk like your mother, you talk like your dad or you talk like your mother. So this process is called inheritance, and we will discuss this process through an example. So the elegance of object oriented programming or object oriented systems is that it kind of tries to replicate the way we are in the nature. So let us have a look at the structural inheritance. I can give some default values to vehicles. I can say that most vehicles cost $15,000. Most vehicles, the exterior color is brown, and the components, the vehicles have a body, a drivetrain, and so on. Now I have defined the class car as a subclass of the class vehicle. And when I ask here what is the exterior color, the answer I will get back from this object is brown. Because this information, remember, is not in this particular object. However, the information exists in a higher level object. So the information from the higher level object is now inherited to this lower level object. On the other hand, if I ask what is the cost, I get $10,000. That means what I have done is inherited structure, and then I overrode the structural behavior. In a similar way, for example, you can inherit certain features from your parents which you may not like. Like for example, you might inherit a long nose or a short nose. You might want to cut the long nose into a short nose, make it medium, and you want to elongate the short nose by a means of called plastic surgery. So this is very similar to this process where you inherit certain structural attributes and values of these attributes, and you change the values of these attributes. Note that in addition to inheriting all these attributes, you can change not only the values, you can also add in new attributes anywhere down the taxonomy. I have a triangle here. I will tell you what the triangle is later on when we come and talk about object oriented software development. For the time being, just understand that this one denotes the subclass relationship. Now if you take the BENZ car, BENZ car is a car, but however I have changed now the exterior color to black. So if I ask the exterior color here, I get the answer black. If I ask the exterior color here, I get the answer brown, because I have inherited brown from here. I have inherited brown from here, but I overrode the brown and made it black. Similarly, I took the cost and changed the cost to $40,000 as such. However, in the Toyota car's case, if I ask the cost, I get $10,000, and if I ask the exterior color, I get the answer brown, because this brown is inherited through this link here. Now I make Mary's car, which is Mary's car an instance of the BENZ car, and I only change the exterior color to red. So the cost remains the same, which is $40,000, and the exterior color is now changed from black to red. If I have Jack's car here, remember Jack's car, the cost is $42,000, so I override that particular structure here. Please note that I'm only describing here single inheritance, and there is something called multiple inheritance, where you can inherit structure from two parents instead of one parent, just like we inherit certain features from our father, from our father's side of the family, and certain features from our mother's side of the family. Similarly, here we can do the same thing. And in terms of the behavioral inheritance, we can do the same process as such, where in this case the way I'm only showing you the behavior and not the structure here. I have two behaviors here, get ID and diagnose. So if I send a message to vehicle called get ID, I invoke procedure get ID. If I send a message called diagnose here, I invoke the procedure diagnose vehicle, and this is a knowledge based expert system which knows how to diagnose vehicles. Take for example car. Now diagnosing cars are very similar to diagnosing vehicles, except that there may be some subtle changes. So the diagnosis of a car is little different than diagnosis of a vehicle. So I define a new procedure here, but the message selector is the same. This is called generally message selector in object oriented programming. And when I send the message diagnose here, the procedure that gets invoked here is diagnose car. I can go further down, and for BENZ CAR, if I send a message called diagnose, I have a procedure called diagnose BENZ, which is very similar to diagnose car with some so diagnose BENZ is very similar to diagnose car with certain changes in here. Similarly, for diagnosing Toyota car, very similar to car diagnosis, except that diagnosing Toyota car has certain subtleties which are not the same for all cars. Okay. One thing you need to note in here is that this is how we have implemented the polymorphism process, where if you send a message called diagnosis here, the procedure diagnose vehicle gets invoked, and then when you send a message BENZ CAR, the procedure diagnose BENZ gets invoked. Now we are now inheriting the behavior along these lines, and we are also overriding this behavior at various classes. Mary's car is an individual object, and we are not changing the behavior here, but we can also change behavior at this level. But in many cases, in some languages allow this and some languages don't allow it. Languages such as Lisp are fairly flexible and they allow changes at this level. Languages such as C++ do not generally allow changes at this level unless you do something to C++, and we will talk about how to do that later on. Now here when we talked about overriding behavior, we didn't mention one thing. That is, what you can do is you can take the behavior that is present in the parent's class and you can reuse the behavior. This is the process of sharing behavior. For example, there are a number of books which they sell in the market called Car Repair for Dummies. Okay. Now this Car Repair for Dummies book may not be suitable for all cars, or it may be only suitable, there may be some generic procedures involved in there. So you can buy the book and know in general how to repair a car, but you may not know the details as such for different cars. For example, you have to buy, if you have a Toyota car, you might want to buy a particular manual that is sold by Toyota people, which have some similarities to the diagnosis of cars in general, but there's some peculiarities to Toyota car as such. So the way this is implemented is through this process called behavior sharing, where now if I send a message called diagnose to car, the procedure diagnose gets invoked, and the procedure diagnose is a knowledge based expert system, except that it is divided into several areas where I can have car specific rules, and there are rules which are common to the to cars, trucks and so on, which are in the vehicle case, these rules are encoded in the vehicle class. So the way I do it is I first write my car specific rules either here or here, but then I also send a message to the parent to invoke the parent's diagnose vehicle in this case, where I send a message called send super, and when I do that, when I use this keyword called send super and I send the message called diagnose, it will go and pick up the appropriate parent in this taxonomy and invokes the appropriate procedure in there. So what I am doing now is I am reusing certain behavior which is defined at the parent level and in the child level, and we can continue this process along in this case. Now I will define another concept called dynamic binding. Now this dynamic binding is a process of attaching a variable name to an object type or a message selector to a method. We have seen in the previous example polymorphism, where if you send a message diagnose to the vehicle car, the procedure diagnose gets invoked. When we send a message diagnose to BENZ CAR, the procedure diagnose BENZ gets invoked. Now, during runtime, what is happening is depending on where I send the message diagnose, the appropriate procedure gets bound to this particular message. Here, this particular message, this particular method gets bound to this particular message. Here, this particular method gets bound to this particular message. So, the binding process is attached. In this case, we are attaching the method to an appropriate message selector. In the vehicle case, we attached procedure diagnose vehicle to diagnose, and in the BENZ CAR case, we attached procedure diagnose BENZ CAR to diagnose. So, that means this associating a method to a message selector is done during runtime, depending on depending on which object or which class that we sent this particular message to. Now, there is another thing that we have not mentioned here is also is attaching a variable name, attaching an appropriate object type to a variable name. So, the variable name and the object type are kind of bound in some way to one another. Now, some languages such as C++ do not allow this for attributes. They do allow it for their methods, but not to the attributes. On the other hand, some languages such as Lisp allow this process where you can determine the type of the attribute during runtime. So, in other words, in languages such as C++, you cannot determine the type during runtime, and the type has to be determined during compile time. So, they do not allow dynamic binding of attributes. However, they allow dynamic binding of messages to methods. In languages such as Lisp based languages, things are a little different, where you can bind the variable to a particular type during runtime. This is a very useful process for doing prototyping, but it may not be that useful if you are developing large scale software development as such, because the types are not known at the compile time, but they are known at the runtime. A related concept to this dynamic binding is this process of overloading. We have not discussed overloading so far, but what in some languages the operators could be overloaded. That means if you have for example, you might have an operator like plus. Now, plus takes two arguments here on either side, let us say 5 plus 4. On the other hand, I want to 5 is a particular object. If we, in object oriented systems, everything is treated as an object. 5 is a particular object of the type integer, 4 is a particular object of the type integer. Now, this plus operator is taking two objects of different types, that is 5 and 4, and it will return 9 to you. Now, however, what happens if I do A plus B, where A is a matrix and B is a matrix? What you can do in many object oriented languages is to overload this plus operator. So, you can the operator can be used for both matrices and integers. That means the operator can take A plus B, where the operator can take A and B as arguments, as operands, where A could be either a matrix, or A could be either an integer, or A could be anything in the world. A could be even a string. So, I can have A as a string, B as a string, but still if I write A plus B, that operator knows what its operands are, and so it acts appropriately, and this process is called operator overloading. So, now we are going to summarize some of the concepts that we have learned. Object oriented programming organizes programs by combining data, which is structure, and procedures, which is behavior. It causes actions through message passing, and we can obtain sharing through the process of inheritance and object oriented programming can be integrated with other paradigms. We did not talk about object oriented database systems, which we will be talking about soon in the next module, and object oriented database systems extend object oriented programming languages. As we were discussing, there are 4 mechanisms of object oriented systems or object oriented programming, that is defining objects, forming taxonomies, sending messages to various objects and invoking appropriate methods, and sharing code through this process of inheritance. And we also defined, along as we were talking about these basic mechanisms, we also talked about several key concepts. And the key concepts that we talked about are abstraction, where we only describe the skeletal structure and behavior and differ the details to a further state. And the next thing we talked about is polymorphism. Poly is many, morphism is forms, where the object can take multiple forms during runtime. And we have seen some examples of that, that is objects kind of respond to different objects respond to the same message in different ways depending on the particular state of the object at that particular time. We also talked about encapsulation, where the innards are hidden from the exterior, or we have a clear division between the private part of the object and the public interface to that particular object. So, the innards are hidden from the outside world, and this process is called encapsulation. We talked about overloading, which is a kind of a polymorphism where both operators and functions are overloaded. So, where is the future for object oriented systems? There are 3 areas which I think the future lies in. And the 3 areas for the future of this object oriented systems are: 1, software factories; 2, collaborative work; and 3, multimedia. Let's take a few minutes and discuss about each one of them. Software factories. You have seen these objects kind of encapsulate both structure and behavior. So, what we can see in the future is just like as we buy parts for cars, similarly we will go and buy software objects. Brad Cox, in his book on object oriented programming, talks about software ICs. A software IC is very similar to the integrated chip that you see on your printed circuit on your boards in your computers. It's just an independent unit. It's a unit where you can go and plug in an appropriate part of your program. I think this trend will play a big role in the future. However, one problem I see is the management of these software ICs in terms of how you are going to get your royalties for your particular software, because there is a difference between hardware and software. For example, the parts, they consume certain resources, they consume certain material, whereas software, in terms of the cost involved in the materials, is kind of negligible as such. The only thing you do is to sell it on floppy disks or maybe some other medium, optical disks, and these are not very expensive items. So, it's going to be an extremely hard thing to manage the software ICs, but however, I think the way we are going in the future, we will see that there will be some way of managing software ICs. So, where people will sell you, just like they sell you printed circuit boards, they will sell you skeletal programs, and you can go and buy a software IC and place them in the appropriate part. It's a little bit of a controversial topic, but it's an interesting topic. The second area is collaborative work. Our ability to compete in the global markets will depend on how well we collaborate in the future. In fact, in the future, I think this particular broadcast will be done in a very different manner via the computers. So, there is a big trend towards computer supported collaborative work, and I believe object oriented systems are going to play a major role in this process. We will, in module 5, show how we have implemented things for concurrent engineering or computer supported collaborative engineering by using by extensively using some of the concepts that I will be presenting in the next 3 modules. Finally, multimedia. We are seeing this trend already in terms of Apple Macintoshes, IBM PCs, DEC machines, and so on, where there is a trend towards selling machines which incorporate or facilitate voice, video, and sending pictures and all kinds of things. So, the trend towards multimedia systems is there, and then we will see this over and over again in various systems in both computers in terms of hardware and software. At MIT, in fact, we have a major program at our Center for Educational Computing Initiative, where we are developing state-of-the-art multimedia system using object-oriented technologies. That concludes module 1, and in the next module I will talk about object-oriented database systems. In object-oriented database systems, I will elaborate on the concept of persistence and show how object-oriented programming programs can be easily mapped onto the physical databases. We will take some examples from engineering, and then I will show you how this particular technology is very useful for solving a wide range of engineering problems. Thank you, and we will see you in module 2. Hi, welcome back to the course on object-oriented systems. During the lunch time, there were a couple of questions, and I will try to clarify the questions now. The first question is to deal with the notion of instance of and ISA. The person asked a question, what is the difference between an individual object and a class object? If you look at the way I have described, they all look the same. Why is that you made a distinction between the individual object and the class object? Now, the primary difference between the class object and the individual object is as follows. In the individual object is a unique object where you cannot subclass or make further clones of these individual objects. So, they are objects which have their own unique identity and they exist in the physical world. Class objects are abstract objects. In other words, these have an identity in the physical world, these have an abstraction in the physical, they do not have an identity in the physical world. The class objects are objects which are an abstraction of the individual objects which have a physical identity and cannot be further subclassed or cannot be further individualized as such. So, individual objects are individual unique objects, and that's the difference between the individual object and the class object. Otherwise, the process of inheritance and all the other things are very, very similar to both of them. In fact, they are the same. The second question is in relation to dynamic binding. What really is dynamic binding, and why is it that a different word that is different terminology that's used for instead of the things which we see in regular compilers? Well, the difference between static and dynamic binding is in dynamic binding we defer the binding process until runtime. That is, during compile time we don't bind the type to the variable or the method to the message selector. The binding is done during runtime, not at the compile time. If it is done at the compile time, it is static binding. Okay, with that, we will go to the next module, which is object-oriented database systems. Well, I hear that we have a phone call, and let me take the phone call right now. Go ahead. Okay, I guess we don't have it. We'll wait until the end, or maybe please feel free to call me anytime. This section is more oriented for engineering applications, and first I'll discuss the nature of engineering problem solving. Then I will give you a scenario on how typical problems are solved in a collaborative manner. We will discuss the engineering data requirements. What are the characteristics of object-oriented database systems that are useful for engineering data requirements? Then we will compare and discuss the advantages of object-oriented database systems over relational database systems for engineering applications. I will give you an architecture of object-oriented database systems for engineering, and then finally we'll summarize. Okay. The engineering process starts with the market needs, where we go and do a data analysis or the market analysis, and you zero in on a particular product during the conceptualization stage. For example, your TV, or maybe your car, or some elements in your car. If you want to have an intelligent vehicle system in your car, incorporated in your car, you say, well, there's a market for it. You do R&D. From R&D, we do design, and design involves coming up with a set of specifications which could be manufactured, and from manufacturing, we go to testing stage. From testing stage, we go to marketing, and from marketing, we go to maintenance. And this process is some kind of an iterative and a collaborative process. In a traditional product development, the way this is done is as follows. I'm taking an example in the architectural engineering construction industry, but this example is the same in most industries. Here, the architect first does the design and throws it over the wall to the designer. The designer then does some calculations and throws it over the wall to the fabricator. We have a manager who is overseeing all these people, and then we have a client who is paying for all the work, but the client is kind of confused as such. Now, in this process, if I take the design and manufacturing process as the one which I described before, I'm only considering the two stages. That's the design stage and the manufacturing stage. The expenses incurred during the design stage are about 3 to 5% of the cost is incurred during the design stage. However, we make 40 to 60% of the commitments during this stage. In the final production stage, we incur 85% of the cost, but we have only can change about 5% of the variables. So we have control over 5% of the variables versus a large number of variables here. So what does this translate to? This translates to the following. If you were to make an error during this design stage, and if that error were to cost you $1,000 to fix during the design stage, the same error would cost you $10 million if you catch it during the production stage. Now, this particular problem is not only for engineering problem solving, but also for software development, as we will see later on. So how do we go about doing it? One way to do it, which is called the shared view, and we will talk about how to implement this during the application section, is that you have a number of agents working together through the computers, and they access a shared database. So what are the characteristics of this database? And that's what we will emphasize. We will put an emphasis from now onwards. Here we have the human beings talking through the computer through the shared database or the shared workspace. And the human and the computer, I call it as an agent. So we have several agents who are collaborating through this centralized workspace or the data space. So if you follow this approach, this is also called concurrent engineering or collaborative engineering. If you follow this approach, then we have several advantages. The advantages are the development time is about 30 to 70% less. The time to market is 20 to 90% less. we have fewer engineering changes, the overall quality is increased, we have return on assets is increased. So, we have a number of advantages, and this was based on an analysis done by the National Institute of Standards and Technology and Institute for Defense Analysis and a host of other organizations found this out. So, let us see how this one will work. Let us go through a scenario and see how this is done in a typical engineering example, where we have a global shared database, and then we have groups forming here. We have an architect, a structural engineer, a geotechnical engineer, and these three people have their own locally shared database, and once they have agreed on some aspects of the problem, they check in and check out into a globally shared database, and then we have a number of other participants who are accessing this globally shared database, and these participants can have further subgroups in there. So, if you look at engineering in such, we have overall we have a number of people working at one level, and we have another set of people working at another level, and so on and so forth. So, this is the notion of nested transactions which happens in engineering. We will come to that in a minute. So, let us see how this what happens in the subgroup, the architect, structural engineer, and the geotechnical engineer. Let us have a closer look at what the architect is doing here. The architect does the preliminary layout in his own his or her own personal database, and then posts it into the shared database. Once the architect posts it into the shared database, the structural engineer is immediately notified that there is something for the structural engineer. So, the structural engineer checks out the house objects, does some preliminary analysis and design, and while the structural engineer is doing this, the architect at the same time is continuing out with the details of his or her layout design. The structural engineer completes the design and posts it into the shared database, and when this happens, immediately the geotechnical engineer is notified that there is something for the geotechnical engineer, and the geotechnical engineer checks out the column objects and begins doing the preliminary design and layout. And while this process is going on, by the way, the structural engineer also gets a notification. So, as people are putting things into the database, people are being notified simultaneously. So, the architect continues this process, and at the same time the structural engineer is being notified, the geotechnical engineering is being notified of any changes. So, this process keeps going on. As this is going on, the architect can make a change to the initial specifications, because in the design process specifications always change. So, the architect decides that the layout that he or she has done before is not appropriate, or there are some initial changes, and they make the changes and post it back into the database. Now, note here, many times we may not want to erase the old version for historical purposes. So, we say that this particular design is versionable, and once we say that, a version is created and then it is tagged on to the previous version, and at the same time the structural engineer is notified of the change, and the structural engineer now checks out to see whether the components are in agreement with his previous design or not, and then if there are any changes, the structural engineer makes the changes and goes and posts it back into the particular database. As he is doing that, now the geotechnical engineer gets notification, who then checks out the new data for possible redesign, and this process goes on and on, where the versions are continuously being created. Finally, the design is completed and agreed upon by all members, if and only if after everyone agrees that the design is okay, and then they post it back into the central database, or the database that we have seen around in this particular slide here. So, once the people agree that once they all agree on the aspects of the design problem, they post it into this local shared database, and from there we post it into the globally shared database. Now, this is a fairly complex process, as we have seen, and what are the data requirements for such engineering problem solving? Well, if you look at it, engineering objects revolve around artifacts, about the notion of an artifact. The TV camera, the TV that you are looking into, the camera that I am looking into, these are all artifacts. So, engineering is really artifacts based or object based. Artifacts are objects. In engineering, we think about objects all the time. These objects have structure. Your TV screen has a structure. Your TV has a behavior, is showing my face in there. So, so these objects have both structure and behavior. And in engineering, we model at various levels of abstraction, especially when we talk about a building. At one level, we talk about just the building as such. At another level, we talk about the 2D lateral load resisting system. At another level, we talk about a 3D lateral load resisting system. And each one of them have some geometric configuration associated with them. Engineering involves complex data structures, complex relationship between various objects. Like your TV, for example, there is a relationship between the tube there, the cathode ray tube, and the housing. That's the TV, the housing for that particular cathode ray tube. Similarly, there are some printed circuit boards in there, and they have a complex relationship to the cathode ray. So, there is a lot of complex relationships between various objects, and these objects are tied fairly in a complex manner, and they are made of, objects are made of one another. Engineering design, as we have seen, is an iterative and collaborative and incremental process where the design objects evolve through an entire lifespan, going through several stages. The tasks and data are shared among engineers, as we have seen in the previous example. So, what are the database requirements for engineering problem solving then? So, the database requirements are shown here. First, we need it to support complex information processing. Second, because engineering objects have a inherent behavior and structure, and they are very rich in terms of there is some semantics involved in there. The database system should support this semantic schema design. I am using the word schema here to mean a collection of objects, and the word schema is used in relational databases in a different way. Since the objects are related to one another, their objects have constraints, like we have a constraint that the cathode ray tube should be within the housing. So, this is the physical constraint which is placed. So, this particular constraint has to be satisfied no matter what happens. As in engineering, as in other places, we deal with large volumes of data, like when you do a finite element analysis program or a SPICE program, you deal with massive amounts of data, and that data has to be stored on the hard drive. Engineering is unique in the sense that we deal with a lot of geometric and pictorial data. One of the major differences between engineering and software is that in engineering we deal with physical entities which have a well defined geometry, and it is not so in the software, as we will see in module 3. The database should support data sharing, data versioning, and change notification. Remember, when the architect made a change and posted it onto the database, that change has to be notified both to the structural engineer and the geotechnical engineer. So, the database should support change notification. Let us look at some characteristics of object oriented database systems that help in this process, that are very useful and intuitive for engineering problem solving. Object oriented database systems are based on object oriented programming languages. For example, the object system provides you with various levels of data abstraction. It helps you with complex information modeling. Objects have identity, and we will come to the identity part later on. Encapsulation and data hiding. We can have active intelligent data by encoding behavior in the data model, as we saw in the car example, where we had a diagnosis set of diagnosis rules in the car objects, and they offer the object model offers inheritance. In addition to that, most object oriented programmings allow polymorphism. Although object composition is not a part of regular languages such as C++, we can augment this with having object composition such as the part of link, and we will talk about that later on. Object oriented systems, as we have seen before, help in the process of message passing. They are extensible and help in the process of incremental development. Some languages help in dynamic schema evolution. And finally, object-oriented programming languages are computationally complete programming languages, and object databases so have the facility or the advantages of this computationally complete programming languages. However, object-oriented database systems extend object-oriented programming languages by providing persistence. That is, you can store the objects which are created in memory on a physical disk. We can have versioning capabilities. They allow cooperative transactions. We will see cooperative transactions later on. We do type-specific concurrency control, recovery, and consistency. In terms of the technological positioning of object databases versus relational databases, we see that in the past we can divide basically the object databases into the fixed model and the extensive model, and based on the query we have navigational query or we have structured query languages. With network based systems have a fixed model and they are based on the navigational query system. The relational databases have a fixed model, but they have a nice structured query language interface to them. The extensible models, the early object-oriented models are extensible in terms of schema evolution or the object evolution. However, they mostly provided navigational facilities, and we are seeing a trend towards object SQL or object-oriented standard query language, and so the object-oriented systems can be positioned around here. Now I will discuss some of the advantages of object-oriented database systems over relational database systems. If you look at the current literature, you can see that the object-oriented the relational database systems are being used quite a lot in many applications, even in engineering problem solving. However, I will show that object-oriented databases are much better for doing the kinds of problems that I have mentioned before. An object-oriented database, object-oriented model is a more realistic data model than the tables. If you are an engineer, you don't talk about tables. This is a table which I am sitting on, which is here, of course, but you don't think about a table in terms of representing the TV monitor which you are looking at. So we think about artifacts. Objects are a more natural thing for us than tables. Object-oriented database systems have object model over them, so they provide a much better and a more powerful data model for doing our complex information processing. These are more extensible and flexible. As we have seen that the object model helps in the process. It's easier to build your schema and dynamically evolve the schema. Some languages like C++ don't allow it that easily, but object-oriented database people have added dynamic schema evolution or dynamic object evolution over C++, so they provide this kind of things. And you end up in a smaller size of schema, a smaller size of objects, because you are using the facilities of inheritance where you can share code, attributes, that is, you can share both structure and behavior. Most of the object-oriented databases are identity-based versus the value-based in terms of the relational databases. The relational databases are value-based, which expresses relationships between two objects by embedding the same value in two or more related objects. So the user defines some unique keys to distinguish between similar entities, and this often results in a duplication of data. The object-oriented systems, on the other hand, are based on identity. What does an identity-based systems do? We relate two or more objects independently of their embedded values. So these things are independent of the values, whereas this is dependent on the values. Now, the identity facilitates the notion of sharing by having references from various points to the same objects rather than keeping copies. We'll talk a little bit about object identity later on. And object-oriented programming languages have computationally programming language as their embedded in them versus the impedance mismatch in relational databases. So what does this mean? In terms of relation, we'll talk about it in a few minutes, but if you look at relational databases, the language that you program in is different than the language which is natural to the relational people, that is SQL. Then in terms of the concurrency control, in object-oriented databases, we can do type-specific concurrency control versus the notion of serializability which the relational people enforce. Now, I will talk about these things after in a few minutes and show you some examples on how the object-oriented systems do these kinds of things. The object-oriented databases have better data versioning capabilities than the relational database systems. They provide greater flexibility for collaborative engineering activities and cooperative work. So in the future, we can see an emergence of object databases being used for collaborative engineering. In object databases, we have intelligent data versus dumb tables in relational. The relational tables have no notion of behavior. They're really, really dumb tables sitting there. They're flat files. Whereas objects have some structure, objects have some behavior, and you can add intelligence to these objects. The query language in object-oriented systems is much more expressive than the SQL that is generally given with relational databases, and we will see some examples of that. So let's clarify these concepts a little more in the following slides. If you look at the relational databases are value-based, where the reference is made by value. We have certain keys, and then we map the various relationships because of the values of these keys. Whereas in object databases, we make reference through object identifiers, which are unique identifiers. Generally, they are known as OIDs. So these object identifiers are value dependent, but of course we can allow sharing because we can have multiple references to the same object. There are several ways that one can generate this object identity, because we said we need some unique object identifiers. One way to do it is to generate the address of the object in the main memory. However, the problem with this process is that once the program dies, that particular address also goes away. So this is not a very useful way of doing it, and it is not generally done in database systems. In database systems such as relational databases, one of the things they do is to use the structured addresses where associated with each table, we can have the volume, the page number, and the slot number on the appropriate disk space. In object-oriented systems, we can have a similar thing where we can attach the structured addresses to objects. I will talk about these examples soon. The other approach is to use something called surrogates. In surrogates, we define the object identifiers are globally generated identifiers which are unique, and they do it using some program which is guaranteed to generate a unique object identifier in some manner. Some object databases use this, but most of the C++ based database systems do not use surrogate IDs. Many of them use structured IDs. Then we have typed surrogates. Some systems such as Orion or Itasca, which is a commercial system, uses this typed surrogate. So in terms of the mapping between the relational database and the object database, if you look at the relational databases, the relational database mapping is done in the following manner. There are three levels here: the conceptual, the logical, and the physical level. Really, we don't like to think in terms of relations most of the time. So Peter Chen came up with this entity relationship model. So we define entities along with relationships between these entities. So this entity relationship model, of course, this model does not have inheritance in there. So it's some kind of still a flat structure, not so flat, but it's not doesn't support inheritance and all these things, and no behavior also is encoded in there. So this is mapped to the logical level, which are the relations, and from there you map it into the disk structures. However, in object databases, there are objects and objects have relationships, and objects inherit information from other objects, and these are mapped directly onto the disk space. So there's a one-to-one mapping from here to here. Now an example which Tom Atwood gives is the following. Suppose you have a Mercedes-Benz. However, you do not have a garage in which the Mercedes-Benz, however the garage door is very small, so the Mercedes-Benz doesn't go in. What you do then is you get the Mercedes-Benz near the garage, dismantle the Benz, and then take it into the garage, and then you can put it back, piece it back together. And that is how a lot of people do nowadays in terms of mapping from objects to relations to these databases. And the reason they do it is because a lot of people have already invested millions and millions of dollars into relational databases. And when we have invested so much money into relational databases, you don't want to throw away your relational databases. So what do? Well, you follow this approach where at the conceptual level we know that objects are a nice way to do things. So we map that objects into the relations, and from there you can use all the advantages of relational databases. Now this approach is fairly good if you have already invested lots and lots of money, that is, you have millions of garages already built, and maybe the cost of disassembling your Mercedes-Benz is not so much. So in that case, you can do this operation going from objects to relations and relations to data structures. On the other hand, if you are starting from fresh, my idea is to go from objects to from object-oriented languages to object-oriented databases. So we provide a seamless integration. Here is another example of that mapping, which is given by Mary Loomis, where you have the relational databases in form of table, and then your programming language uses this SQL type commands to get the information and puts it into a memory structure, makes some changes, again using some SQL type commands, you put it back in here, and this is called the impedance mismatch. Whereas in the object case, what we do is we directly map from the memory into the object-oriented database systems, and we do the operations in the memory, do a one-to-one mapping, and we will come to this particular example in a minute or so. The next example that I would like to talk about in terms of the differences between object-oriented databases and relational databases is the query example. In object-oriented databases, we have an object model. So the object model for our vehicle case looks something like this, where we have a vehicle here, and then I have not shown the behavior here, I have only shown the structure of the object. Remember here really we are discussing the relational model and the object model. So let's look at the object model for the vehicle again. So the object model for the vehicle looks something like this, where I have the ID, type, color, drivetrain, and this drivetrain is some kind of a composite object here. So there's a reference to vehicle drivetrain, which consists of an engine and a transmission. So the engine is of the type vehicle engine. Drivetrain is of the type vehicle drivetrain. Engine is of the type vehicle engine. Manufacturer is of the type company, which has a name, location, president. And the president is of the type employee, where you have a social security number, name, age, picture, and we have several methods and constraints that we can invoke on this particular employee. The ESA relationship now I have shown by these thick lines, and the references I have shown by these thin lines here. In traditional relational systems, a relational model, because of normalization, we cannot do that. So we have to take this rich complex structure and then break that down into some flat files. So I have broken the objects into the following flat files: vehicle, company, and employee. and my identifier, the way which I point from vehicle to employee is through this manufacturer, which is a foreign key to the vehicle, and vehicle ID is the primary key here. So the foreign key is between the manufacturer here and the employee here. So the manufacturer name, the manufacturer here and the employee name have to match. So if you were to make a query then to find out the vehicle, all the vehicles whose color is blue and whose manufacturer's location is Detroit, and whose president's age is less than 50. So you want to get hold of all the vehicles whose color is blue and whose manufacturer is located in Detroit and whose president's age is less than 50. The way you do that in an object-oriented model is the following. All the object-oriented programming languages do not offer the query support. Object-oriented databases augment object-oriented languages with the database support. So in this case, we send a message called select to the collection of vehicles with the following argument here, where vehicle.color, see the natural way you are doing it, you are saying vehicle.color equals blue and manufacturer.location equals Detroit and president age is less than 50. So this query is some kind of a navigational query. On the other hand, even for the simple example, in relational database systems, I do it in the following manner. Select vehicle.id from these three relations, vehicle, company, and employee. Remember here there is only one object, one class object here, which is the vehicles, where vehicle.color equals blue, which is similar to that. However, now we have to tie the employee and the vehicle, and so the company and the manufacturer. We do it by vehicle.manufacturer equals company.name. So that's how we do this tying in here. If you go back to the previous slide, here the manufacturer is tied by the name attribute of this company. Similarly, the company's president is tied by this name here. So we are tying the manufacturer with the name here, and we are tying the president with the name around here. And we can have one more attribute around here, and in this attribute we can even say vehicle owner, and the owner can be tied to the name here. So the owner can be tied to the name here, the president is tied to the name, and the manufacturer is tied to the name of the company. Now you can see that this is a pretty complex thing, and we can get a lot of confusion even in a simple 3 tables. We can get it, it's pretty confusing as such. Now then we have company.location equals Detroit and company.president equals employee.name and employee.age is less than 50. So this is how we do a relational query, and when we do that, we end up with a lots of selects, join, and project operations. Now I have a feeling that for many of the engineering operations or engineering queries that we are going to do, the object-oriented model is in a worst case maybe as bad as a relational model, but on an average case it may be much better in terms of efficiency than the relational model. Again, this is my feeling, and we hope to show that in the future. Next, I will discuss about object-oriented database architecture for engineering problem solving. And this is very similar to some of the architectures which are again found in the relational world, because the object-oriented databases, many of the database systems have been influenced by some of the work which is done in the relational database world. And these are the architecture that you find most of the time is the client-server architecture. In the client-server architecture, we have clients here which communicate through a centralized server. There are 4 basic components that are generally available in all object-oriented databases. One is the object manipulation capability. Generally, this is part of the programming language with some augmentation. It's a query module, a storage module, and a transaction module. In some systems, the storage module and the transaction module are at the server level, and in some systems, such as the Itasca or the Orion, these modules are both at the client level and at the server level. In some object oriented database systems, we can do object or schema evolution at the server level. In most of the other, in many systems which are based on C++, you cannot do that, and we'll see why not, and we do that at the client level. Similarly, querying, we cannot do it at the server level in many systems, we do it at the client level. So there are different variations of this architecture. What I'm going to do now is to take a couple of these things and give you some examples of the transaction system and the storage system. Let's look at the transaction system. As we have seen, multiple engineers can access the same objects in the database. Now, one of the major differences between the financial systems and the object-oriented and the engineering systems is the following. In financial transactions, we enforce the ACID notion, that is, the transactions are atomic, consistent, isolated, and durable. Now, to do so, they enforce what is known as serializability by something called a two-phase commit protocol. So if you use the two-phase commit protocol, you can enforce serializability. However, serializability has certain problems for the group transactions as such. The major problem with serializability is it is too restrictive, as we will soon see in an example. So the transaction framework for engineering then should support collaborative transactions if we are talking about collaborative engineering. So these are some of the features that we require for engineering, and some of the object-oriented database systems support a few of them. Some of them don't support any of this, and we will talk about that later on when we compare object-oriented databases in module 4. One of the most important things here is that we have to define transactions dynamically during runtime, so that we don't know previously what kind of transactions the engineers are going to do. So these have to be defined at runtime, and the transactions are nested, as we have seen before. We have to handle conflicts. Here is an example of a non-serializable transaction as some of the things that we will see in engineering. And in this example, we can see an architect here and maybe a structural engineer here working on a flooring system, like the flooring system that you are being seated on. Now the architect is trying to work on the floor, and the architect read locks the floor because he or she wants to work on the flooring system, but they're only interested on the interior layout and not at the structural details. Now the structural engineer is interested in doing this structural design on that floor, like they want to do, like put in the right reinforcement in the slab and things like that. So the structural engineer requests a write lock on this particular floor. So the structural engineer sends a message to the architect saying that I want a write lock. Now the architect is notified of this particular event, and the architect may unlock the floor system, and immediately the structural engineer is notified that, okay, now this thing is free for you. So the structural engineer at this stage gets a write lock on the floor and goes about designing the slab, and this has no effect on the floor dimensions. However, after he or she finishes this, they update the flooring system by posting it onto the database. Now the architect at this stage read locks the floor and goes ahead continuing with the interior design. Now this process keeps going on. Note that here this is non-serializable because in a two-phase protocol, all the locks are attained in one phase and they are released in the second phase. Here we get the locks, release the locks, and get the locks, and we mix them and we mix all these locks as such. So this kind of thing cannot be done using the traditional database management system framework. However, we can probably enforce this on the object databases, as we have done in our laboratory, where we have developed a collaborative transaction management systems. The other collaborative transaction management systems, which are developed at Columbia University, Brown University, and a host of other places, which incorporate some of the features that I have talked before, where we have lock management, deadlock management. We should have communication facilities, version management. Many database systems such as Object store offers this version management, and we will soon see how it is done. Conflict management, because you can encode constraints in the object. As a result, you can have enforced conflict management. Now I'll briefly talk about some storage servers. So in the architecture of the object-oriented database system, I said there are four components: the query system, the object system, the transaction system, and the storage system. Just now I gave you a feel for how the transaction system should be, and now I will talk about the storage management and discuss how this is achieved in some of the commercial database systems. So we can really divide the kind of storage servers that are available in the market into four types. The first type is called typeless page server. The second type is typeless object servers. The third one is tuple-based object servers. And the fourth one is type-based object servers. So what's the difference between these four? I'll come to this particular slide later on by explaining to you how things are done in a traditional database management system. If you look at the traditional DBMS, this is how the access is done. Suppose the application program requires a particular object or a table. I'm just mapping the tables and using the tables and objects here synonymously at this stage, because we are in the realm of object-oriented databases. Now the application program here requests a particular object, so there is a buffer pool for the database management system. So the application program looks into the buffer pool. If it is not there, it requests the server to give the particular object. So because it's some kind of a structured ID exists, so from using the structured ID, I can go to the disk and get the appropriate page in here. So I get the appropriate page in there, and from here, the representation here is different than the representation which I use in the application program. And this particular object is now translated, the data structure of this object is translated into the data structure of the application program, and it is used by the application program. And after this is done, it is translated back into the buffer pool. So there is a translation process from the application program memory into the database management system buffer pool. And from here, I send it back to the server or disk storage. Now this is kind of little inefficient as such, because there are a number of translations taking place. These particular slides are taken by an excellent book by Cattle, who discusses and compiles a number of object-oriented systems. In object-oriented systems, we take the object IDs, and the object IDs belong to a particular page, and they are directly swapped into the application memory, and by means of some pointer swizzling, we get the representation from the OID, that's the object identifier, into the application memory, and then we directly swap it back into the disk storage. What I've shown this example before when we talked about mapping the vehicle from the database to the application memory, and here I'm giving you a little more detail. And the way this is done, again coming back to this particular slide here, we can see that in the typeless page servers, what happens is that the page as a whole is taken into the application memory. The entire page is taken from the database into the application memory, and the application then operates on the objects. That means the methods associated with the objects cannot be executed at the server level, but the whole page is taken into the application memory, and then you manipulate on the objects, and there are methods associated with the objects which can be invoked at the client level. Examples of this are the Exodus system, which is a public domain system from University of Wisconsin-Madison, and we use that quite a lot in our work, and it's a very powerful system. Object Store is a commercial system which uses the same thing, and it's again we have used this in a number of applications, and I will describe Object Store later on. In the typeless object server, the unit of transfer, instead of being the page, it's the object. However, these things also have no notion of the class of the object are how to execute the object methods at the server level. The tuple based object servers are extensions of the traditional relational database systems, except that they extend the relational database model with the object model. The type based object servers are the most flexible of the lot, where you can type based object servers where the objects objects at the server level can be manipulated, and you can manipulate them both at the server level and the client level. So these are very flexible. However, there is some overhead associated with them, so they tend to be a little slow for some of the applications. Here is an example of how Exodus goes about doing its work, and this is kind of a little tricky around here, where we create a unique object identifier, and associated with this unique object identifier we have a page ID, a slot ID, and a volume. The page ID tells you, the volume ID tells you where in the disk storage this one exists, the volume or the segment in the disk storage. The page ID will tell you what page it belongs to, and the slot ID will tell you the offset in this particular page where you can get. And there are two other numbers here, the unique and the offset, which are very little more complicated now to discuss through. However, this is to suppose this object is deleted, it makes sure that there are no duplicates, references to this object. So here we take the object ID and transfer it to the server through this process, where there is a unique descriptor, user descriptor hash table, and this is mapped to this hash table. From there it mapped it into a unique user descriptor buffer pool, from there to the storage manager buffer pool to the disk storage. The actual process is a little more complex than this, but I have tried to simplify around here on the mapping from the OIDs from the application program to the server level. So this is a little detail which if you are interested in more information, you can get it from University of Wisconsin-Madison and talk to them directly on how you can get this. There's another package called the Orion. Orion is a research system which is developed at MCC, and the storage manager looks, and then now they have commercialized it as Itasca, and we'll talk about it a little bit later. And it has the storage manager there has several components like the access manager, object buffer manager, the storage manager, and the page buffer manager. So in case you need a particular object, the way you go about doing it is to call the storage manager. The storage manager first look into the object buffer manager. First call the object buffer manager to see whether it's in the object buffer pool. If it's not there, call the storage manager. The storage manager goes and calls the page buffer manager. So the page buffer is taken from the disk space and put it into the page buffer pool. From here, the access manager takes it and then puts the right objects in the object buffer pool. And here is an example of that process, where in Orion, Orion is one of the systems which is a type-based object server, and it uses some kind of a identity called the surrogate ID. Again, this is a fairly complex process, and this is called the typed surrogate. I'll try to explain that in a couple of minutes. The objects are not directly referenced in this case, but rather through in the object buffer pool, we create something called a resident object table. The resident object table consists of a number of descriptors, which are unique IDs here, 1, 2, 3, 4, which are again hashed into this. Now these UIDs point to these UIDs point to another data structure called an ROD. So this is the ROD here is called resident object descriptor. So the resident object table has got elements which point to this resident object descriptor, and this has the pointer to the actual object. This also has a pointer to the class object, and that's one of the reasons that is one of the main reasons that in Itasca you can execute the methods in the class at the object level, because there is a reference around here. You can do it both on the server level and at the client level. And there are a number of things here to make it more efficient. You have the message cache, log cache, and you have a number of other flags and attributes attached to that, so that you know whether this particular object ROD points to a particular ROT, or if something has changed or some other application program has changed this object or not. So it keeps track of all these things, and this is a very complex structure here, and this complex structure makes it very flexible, but also it also makes it a little slow to run. Finally, to summarize, object-oriented database systems extend object-oriented programming languages by providing persistence, concurrency management, query management, and recovery facilities to object-oriented programming languages. So you have programming languages such as C++, and there are R Smalltalk, R Lisp, and then associated with these programming languages, you have a direct one-to-one map, that is the object-oriented database systems. And these database systems, they help or extend the object-oriented programming languages. So the typical applications for these object-oriented databases are computer-aided design, computer-aided manufacturing, multimedia, hypermedia, operating system, groupware, office information systems, and so on. So what is the future for object-oriented database systems? Well, the future is as follows. One of the things that you might see is, because of the investment made in relational databases, you might see an emergence of hybrid relational and object-oriented systems. However, we may not take these hybrid systems should function as the best of the both. That is, the hybrid relational object database system should be as good, in the relational part should be as good as the most commercial relational database systems, and the object part should be as good as better than the commercial object-oriented database systems. And let us see whether that will happen or not. Thank you, and I will see you in module 3.